So, what's up mga ka-che? It's Kuya Dale here and I'm back with the last part, probably the last part of our chemical engineering thermodynamics lesson. And for today, we will be solving the ideal Rankine cycle and the refrigeration cycle. So, that will be the last part of our lesson. So now, let's go to the lesson. Okay, so we're given here a simple ideal real Rankine cycle that operates such that the condenser produces saturated water at 70 degrees Celsius. So water is compressed to 5 MPa and heated in the boiler to produce saturated steam. So assume pump and turbine to operate isentropically, and then we have to use the following steam table. It's in the next page. You have to calculate the following. So the quantities of steam from the turbine. Okay, so quality of steam, so meaning x, so x prime, let's call that x prime because it is operating isentropically. And then the thermal efficiency of the cycle, and then the mass flow rate. And then if thermal efficiency of the cycle is 25%, so we're still calculating for the steam quality. Okay, so for the here is the steam table data that's given from us from the MRII reviewer. So I'm still using that. So here is the table that they have given us. So now let's go to let's draw our system. So let's draw our system. So it was said that we have a simple ideal Rankine cycle. So what does an ideal Rankine cycle comprise? So it consists of a pump, di ba? Pump kanina, pump. So we have a pump, and then we have a boiler. So okay, so boiler. So we have to heat the water to produce superheated steam or saturated steam, and then that steam will go to our turbine so that we can produce power. Okay, so and then we have our power, this power here, and then that turbine, that steam will go out of the turbine as saturated vapor. Most likely it's most of the time it's saturated vapor, and then it goes to a condenser and for it to produce a saturated liquid. And then after the condenser, it will be sent to the pump, so that it will be pumped to 5 MPa, diba? 5 MPa, and then the cycle goes on and on. So let's number our states here. So we have 1. It's actually up to you how do you but I personally prefer this numbering. Okay, so we have here after the pump, diba? After the pump, it was said that it was at 5 MPa, 5,000 kPa, and then the temperature is not yet we know that this at 70 degrees Celsius, diba? And then after the boiler, so after the boiler, we know that the pressure is still the same. Okay, pressure is still the same, but the temperature is increased. So if we see here in our steam table, it has reached 263.99 degrees Celsius. So let's record that there. And then after it has gone through the turbine, so it was went out as saturated vapor at 70 degrees Celsius. Okay, 70 degrees Celsius, and its pressure is 31.19 kPa. Okay, and then after it went out there, it became a saturated liquid which still has the same pressure, P1, because this of course at same pressure. And then was told that it was still at room at 70 degrees Celsius, and it's now a saturated liquid. So now, so let's so SL here, it's as SV. So here it's also SV. SV hapon na siya. And then here is a compressed liquid or subcooled liquid. Okay, so that's the states of our steam here. So now we are asked 43. So we are asked the steam quality, di ba, after the turbine. So X4. So at X4. So remember that in a turbine, it operates isentropically. So they're given here. So isentropically. So meaning our our entropy here at S3. So we have let's draw the system first. Let's isolate the turbine. So we have here, let's list H and S, and then H4 and S4. So it tells us that it operates isentropically. So meaning, whatever the value of S3 is, it is equal to the value of S4 prime. Okay, so because it is isentropic, so it has the same value of entropy. So that's what isentropic means. So let's from the steam table. From the steam table, you can see it here. Our S3. So S3. So S3 is equal to actually here, diba? This is S3 because this is before the turbine, diba? And then S3 is equal to S4 prime. Okay, and then we have our H also. We have to get our H. Let's get them all here. We have our H here, so this is our H3. Okay, but we don't have our H4 yet. Okay. So let's go back here. So like we have 2,794.3 kilojoules per kilogram, and then we have 5.9734 as our, and then it has the same value of, because it is isentropic, diba, 4, and then we still have to find our H4 later, but we can find that later. So how do we solve this? We have this formula. So we have S4 and then SL, saturated liquid at that temperature, and then SV, or the entropy at saturated vapor, and then entropy at saturated liquid. That's how you solve it. So SL, so SL we don't have and SV. So SL actually is skinny. SL. This is SL and SV. Diba? After naman sila sa turbine. So this is for the saturated liquid and this is for the saturated vapor. Okay? So because just take note of the temperature. The temperature after the turbine is 70 degrees Celsius. Okay? So SL is 0.9549 and SV is 7.7553. Okay, so input that here in our formula. Have 5.9734 minus 0.9549, then 7.553.9549. Then you can get the quality, the steam after the from the turbine. You can get 0.74. Okay, so that's letter C in our choices. Okay, so now we'll have to get our thermal efficiency of the cycle. Let's go to number 44. So eta thermal. Okay, so thermal cycle na siya. So the formula of eta is 1 minus the W net or the network. So let's put that in absolute value so that dili siya mag-negative. Okay, and then take the input nga heat, diba? So that's the efficiency of the thermal cycle. So what comprises of the network? So I forgot to put here, we have a work pump. Okay, so magbutang matag because we are using energy to operate this pump. So we have net is equal to WP plus W turbine. Okay, so that's the work produced by the turbine. So now WP. So how do we find the WP? So actually we have, how do we find that? It's actually the difference of the enthalpies here from the H2 minus H1. Okay, so and they are in saturated liquid, diba? So liquid ta magtanaw. So here we have our so compressed man, so this is H2, and then saturated, this is H1, diba? That's H1. So H2 minus H1, so meaning, so let's 297.16 minus 292.98. So that's 4.98 kilojoules per kilogram. So for our turbine, we have H4 minus H3, diba? Ganina, H4 minus H3, but we don't have, we have H3 but we don't have H4 yet. H4, how do we get H4? H4 is HL, so that's saturated liquid, plus the quality times the difference of, or the latent heat of vaporization. That's how we get it. So H4, diba? HL, so HL, kini HL, this HL, which is H1 also. HL, because take note that we are operating in the 70 degrees Celsius in temperature, and then we have our HV, which is HL and HV. Okay, so we have 292.98 plus we have our X here, 74, and then let's HV is 226.8, and then minus 292.98, and that's equal to 2020 kilojoules per kilogram. So if you get the network, it's the W turbine muna din. So turbine, so the turbine produces so H4 is 2020 minus H3, it's 2794.3, that's negative 774.3 kilojoules per kilogram. And then if you get the network, so 774.3 plus 4.98, you will get 769, negative 769.32 kilojoules per kilogram. Okay, so let's get the Q in. So Q in, Q in is the heat, diba? Produced heat that was needed to heat up our water to steam, diba? This is actually here at our boiler. This is a Q in, diba? Q in. So that means we have to get the difference of H3 and H2, diba? So Q in is H3 minus H2. Okay, we have H2 kanina, diba? And we have H3. H3 is equal to 2794.3 and H2 is equal to 297.16. Okay, and then we have the Q in. Q in is equal to 2497.14 kilojoules per kilogram. And then you can get now the efficiency. Efficiency is equal to 769.32. Remember, it is the absolute value, and then divide by the Q in, and then you can get a 0.31. That's letter A in our choices. Okay, so now we'll get the mass flow rate. This is actually simple. So simple as it is. Diba? So, okay, so let's go to number 45. So number 45, we have to get the mass flow rate. So mass flow rate is actually the work produced by the turbine, and then the difference of the enthalpies. Okay, so we are told that we are to produce 500 kilowatts of power using this cycle, diba? So net, this is net. So let's put 500 kilowatts here and then get the difference, diba? So H4 minus H3, this is 774.3, diba, ganina? So let's put that in absolute value because there is no negative nga mass flow rate. So that's 0.65 kilograms per second. Okay, and that is letter B in our choices. Okay, that's actually simple. And lastly, we have eta thermal 0.25, diba? So let's work that in our equation. So to find our x prime, x sub 4 prime. Okay, so we have you're given here the 46. So you're given here x4 when NTH is 0.25. Okay, so let's substitute that here. So Q out and Q in. So this is actually another form of our efficiency. So the Q out divided by the Q in. So that's how we get also the efficiency. So that's one another way of getting it. So we have a 0.25 here, and then Q out. Q in, we have here, di ba? Money Q in. So 2497.14, and then you can get the Q out equal to 1872.855 kilojoules per kilogram. So we know that Q out. So Q out based on our diagram is here. Q out. Heat is released here because the steam is going from a saturated vapor to a saturated liquid, so it has to give up its latent heat. Okay, so it is the difference of the enthalpy at state 4 and then a different the enthalpy at state 1. So let's put that here. So H4, and remember this is all at isentropic gihapon because we are assuming that the turbine is operating isentropically. So H1. So we don't have H4 yet. So we have 1872. So substitute what we know. We have H4. We don't know that yet. That's what we are getting here. And then we have 292.98. So get H4 by difference, or add that to the Q out. That's 2165.84 kilojoules per kilogram. And then from there, so remember the H4 prime na equation ganina, plus x prime HB minus HL. Okay, so substitute 5.84 plus 292.98 plus x times 2626.8 minus 292.98. Okay, so now you can get your x prime. Just shift solve to find your x. That's 0.80. And that's the third D in our choices. Okay, so as you can see, all of the choices were selected, but that's a different number. Okay, so now let's get to the last problem that I will be giving you. We are dealing now with ideal vapor compression refrigeration cycle. So we haven't been taught this anywhere. Wala si ko tuloy ani sa review, but I learned it on my own. Okay, so we have a refrigerant 134A, and it operates between 0.1 MPa and 0.8 MPa. So using the data below, we have to determine the quality of the vapor from the throttling valve, and then the coefficient of performance, or COP, and then if it is the throttling valve is replaced by an expansion turbine, we are to calculate the new COP. So actually, how this works is just the same as the ideal Rankine cycle, but it is different in components because it is refrigeration. So we are also given the thermodynamic data of our R134A. So let's draw the what comprises of a ideal vapor compression cycle, refrigeration cycle. So the components of a refrigeration cycle is actually we have an evaporator here, and then once that evaporator here, actually the evaporator, this is what collects the heat of the leftover food. Siguro if you have the leftover food from last night and you put it in the refrigerator, the heat of that will be used to heat the refrigerant, so the R134A inside the coils of the refrigeration cycle. So let's have QC here because the heat is so little here that it hits up the refrigerant that quickly. Okay, so we have also our compressor here. We have our compressor. So we have our work in here. because we are using electricity to compress our refrigerant. And then after that, we are going to condense our liquid because it is gas at this point. Condenser, and then we are that the condenser, actually this is found in the kaning likod bitaw, so it's the found at the back of your refrigerator. That's what is really hot bitaw. It is actually used for drying your shoes or your clothes if you didn't have the time to dry it outside. So this is the heat that was collected from the inside of the contents of the refrigerator. Okay, so it 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 throws or it expels the heat outside through the condenser. And then lastly, the liquid goes through a throttling valve. Let's draw that properly. And then it goes back to the evaporator. So as you can see, there are no what will happen in the there are no moving parts of the throttling valve, so it will not produce work and it will not require work also. So that's what the throttling valve does. So it expands your it's also your liquid. Okay, so para makuha siya ang evaporator, so and it goes on and on. So let's number our states. So let's will how we will number it. So this is 1, and then 2, this is 3, and this is 4. Okay, so it is also helpful to draw the TS diagram so that we will be guided on what we will do. Okay, so we have that. So TS diagram. So we have here our phase. So this here, diri mga superheated vapor na ni diri ang compressed liquid. Okay, so the vapor compression cycle has this diagram. So actually dito magsugod sa 1, di ba? So it starts as a 1 saturated vapor, and then we will mahimo din siyang superheated vapor sa 2, di ba? Diri mahimo siyang superheated vapor na. Mahimo siyang superheated vapor, and then will go down here sa condenser nato mo mahimo siyang saturated vapor, saturated vapor, and then because it will be condensed, so mahimo siyang saturated liquid, di ba? Saturated liquid, this is actually our state 3. Mahimo siyang di kini ni after then ana adto din ta sa throttling valve. So this atong throttling valve kini nga step, this is 4. Okay, so that's how it goes. So 1, 2, and then the cycle repeats. Okay, so this 4 to 1, di ba? 4 to 1 diha mag-absorb og heat ang ato ang refrigerant, and then cycle step 2 to 3, that's where our heat is expelled. Okay, and then for 1 to 2, this the enter of the requirement of our work. Okay, so that's how the it works. So now let's list what we know. So we have at state 1, diba? At state 1 we have 0.1 MPa. So it's because it's a saturated vapor at this point. So saturated vapor. So we have this, and then we have this because saturated vapor, and we are to get also this. Okay, and also this one. So what's important here is the entropy and enthalpy. Okay, so we have a temperature of negative 26.43 degrees Celsius, and then we have our H1 and S1, 231.35 kilojoules per kilogram, and then we have 23.95 kilojoules per kilogram. And then we have our state 2. Diba, state 2 is superheated vapor. Diba? So, superheated vapor. So, 0.8 MPa. And then if you can notice, the S is actually the same. So, it is an isentropic step. Diba? The S2 is equal to S1. So, we have equal value here. And then its state is HV, superheated vapor. So let's look for our H2. H2 is diba, isentropic man. So meaning we are to interpolate, diba? We are to interpolate kining mga values, because we are 0.9395 is between these values. 9395. Okay? So we can also get the H2 here. Because we are told that we have to have the same entropy. That's why we are interpolating. So if you don't know how to interpolate, so actually this value of H2 here is 274.33 kilojoules per kilogram. And then if you don't know how to get that, just follow these steps. Mode 3.2 lang gihapon, and then 9374, and then 273.66 dayon 0.9711, and then you have 284.39. Okay, that's how you get it. And then to get the 274.33, just type this into your calculators, then shift 155 to get the y hat, then you can get 274.33. Okay, so now let's go to your P3. So P3 is actually 0.8 MPa gihapon. So 0.8 MPa gihapon na siya. And now it's now at a saturated liquid. Okay, saturated liquid. So you can get the H3 here. H3. So H3. So let's name kanang small nga H because it's a liquid. So H3 here is at saturated liquid, kini 93.42, and then our entropy is kini liquid. So S3 H3 and S3. So you have 93.42 and then 0.3458. Okay. And then we have because this is an or a throttling valve. Okay, so this throttling valve actually operates at state 4. State 4 we have we don't have data now, but we know that it operates isenthalpically. So throttle operates at isenthalpic process. So meaning H4 is equal to H3. That's what it means. Okay, so isenthalpically. So that's now. Let's go to our quality. So quality. So X4. So after that, from the throttling valve now, so we have H4 minus HL. So similar to what I have done. HV then HL. So H4 we have a 93.42, diba? But HL we don't know, but we can get it from the table, the refrigerant table. So what is HL here? HL is this, di ba? 16.29 kini. And then the vapor is kini. Kini ra. Kini lang duha. So 16.29. Then HV is 231.35 minus 16.29. So X4 0.36. That's letter C. Letter C in our choices. So now let's go for the COP, or coefficient of performance. So 49. So COP is actually for a refrigerant. So I've shown you this, diba? So QC over the work in, that's the coefficient of performance. So QC, diba? QC is here, diba? H4 minus H1. So H1 H1 minus H4, H4, and then Q in, W in is H2 minus H1. H2 minus H1, diba? So H1, we know H1 is 231.35 minus H4, we have 93.42, and then H2, we have 274.33 minus 93.42, diba? Kini. So we get 231.35. So can get 3.21. Okay, that's how you get the COP for number 49. So number 50 is actually a different scenario, because we are told that the throttling valve is to be replaced with a turbine, diba? So let's draw the same system. We have a C here, and we work in, and then we have a condenser, and then we now have a turbine here, diba? Turbine. So meaning it produces work now. Produces work, and then go back to the evaporator. So let's number our steps. We have 3, and then we have 4. Okay, so let's find the quality of the vapor here at our turbine, after the turbine, diba? So remember that turbines operate isentropically, okay? Ideally at isentropic conditions, okay? So the this formula is mag-recur na sad siya, okay? So SL, okay? So S4, as you can see here, so S3 na sad is kini diri, di ba? S4 is equal to S3. So S4 prime is equal to S3. So S4 now 0.3458 minus haman ang liquid na to. Kini liquid, and then atong vapor. Okay? So that's our SL and SV. Okay? So we have 0.0678 here, and 0.9395 minus 0.0678. You can get 0.3189. Okay, so let's get our isentropic na enthalpy, diba? So HL, yan, more hapon HL plus X prime, and then HV minus HL, diba? HL still 16.29 plus 0.3189, and then 231.35 minus 16.29. Okay, so get the H4. We have 84.87 kilojoules per kilogram. And now we are to get our QC, di ba? QC, so that we can get our COP. COP is QC over in, di ba? Work in, or in this case now, it is W net, because we have to add our W in and W out. So QC is, don't forget, it is here, QC. So H1 minus H4, diba? H4. So let's substitute 35 and then minus 84.87. Can get 146.48. And then we have our net, diba? W net is equal to W sa ato ang compressor plus the work sa ato ang turbine. So here we have H2 minus H1, diba? Kini H2 minus H1 and H4 minus H3 plus H4 minus H3. H4. So let's substitute 274.33 minus 231.55 plus 84.87 minus 93.42. So get the network, can get 34.23. So substitute that here. We have QC over W net. So we have 146.48 divided by 34.23. You can get the COP, the new COP now at 4.28. That's letter D of our choices. Okay, so we have COP here kanina. Okay, so that's 3.21, diba? 3.21, that's letter A. Okay, so as you can see, the COP gets larger, or it's better if you use a expansion turbine, diba? Kung it's expansion turbine, imuhang gamiton as instead of a throttling valve. Okay, so that ends our lesson for this time. So I hope you have this have helped you in your study. And then actually I will have a bonus content for chemical engineering thermodynamics, but just keep posted of what I will upload next time. So that's it. Bye. Annyeong.